Good afternoon, everyone. My name is Cao, Assistant Professor from Ronstek University. In this talk, I will present our work StegoNet, turn deep neural network into a Stego-Malware. I will first introduce our motivation and threat model, followed by the design spotlights on payload injection and the Logits Trigger. Then, I will discuss our security analysis and use summary to conclude this talk. Nowadays, the neural network has achieved a great success in many different domains, such as computer vision, robotics. Now let's break into the neural network from a system design perspective. The neural network-based machine learning system usually consists of several layers, includes the DNN model, the computing framework, and the computing substrate. Such a machine learning system can be scaled to fit different application and scenario. However, security vulnerabilities can be also found in each layer. For example, adversary attack can fool the neural network to give the incorrect answer by inject perturbations on the neural network inputs. Besides, neural network model functions can be also abused to steal the user privacy. In addition to these security concerns, we found several new attack vectors that can be used for a brand new attack in machine learning system. The first attack vector is a plug-and-play DNN model. Users prefer to use the pre-trained model from internet. However, it can be also abused by the untrusted provider to upload and propagate the bad DNN models. In particular, community usually use conventional serialization and the deserialization process to deploy the pre-trained DNN models. Attacker can take advantage of the insecure deserialization add untrusted code in compromised model functions. The second attack vector is the complexity of DNN models. Attacker can easily hide the bad data given such a huge and complex data space in DNN model. However, the DNN model maintains the nature of obfuscation. We can never understand the meaning of DNN model parameters. It will be difficult for us to identify the slight modification on DNN parameters. Put these two attack vectors together, a significant chance to mix data and code in DNN models, that is to create StegoNet. Now let's look at our threat model. In our threat model, we define the attacker as an untrusted DNN service provider, the end user as a non-machine learning expert. Attacker will inject the malicious code into model parameters and create an attack trigger to extract and execute the payload injection in feature. This created StegoNet will be downloaded by end user and disguised as a normal DNN services. The predefined input can be used to trigger the attack on the user side. To better understand the StegoNet, we compare it with the traditional image-based Stego-Malware injects malicious code into image pixels and using replication to monitor the malware image. These purposes are similar to the payload in StegoNet. However, the attack design in StegoNet is more complex. For example, we need to maintain the DNN accuracy rather than image visual quality. Also, we need to carefully handle the uncertainty on the cyber-physical input. Take this into consideration. We further discuss our design constraint. The first constraint is accuracy. Modifying the DNN parameter can cause significant accuracy degradation. Besides, DNN structure and model size can be scaled. For example, we have only limited embedding space in the highly compressed DNN model for the IoT scenario. The second constraint is the trigger control. We want to precisely control the trigger and trigger events. For example, we cannot use the direct input as a trigger due to the input variation from physical world. Also, we cannot use the direct output as a trigger due to the high false positive rate on the normal input. Our design needs to carefully address these constraints. Let's first look at our payload injection. We tested the traditional ASP used in Stego-Malware. As expected, it cannot handle small-scale DNN models and suffer from accuracy damage. To fix this issue, we further proposed several DNN-oriented payload injection. by leveraging the DNN model structure and training. The first approach is resilience training. Given a DNN model, we first to replace the value on selected parameters using the binary from Payload. This manipulation will degrade the DNN accuracy. Then, we will retrain the DNN model and meanwhile to freeze value on these selected parameters, but to only update the other normal parameters. After a few training shots, accuracy can be rectified. The other two approaches are based on policy. In value mapping, given the payload boundary, we try to search a parameter to find the perfect match. If no perfect match, we will identify the parameter with closest match and modify the value of parameters with the payload binary. The value of matched parameter can be used to recover the payload. The sign mapping is similar to the value mapping, but we search a sign bit rather than the value. We further discuss the trigger design. As aforementioned, we cannot use the input and output from the neural network. Instead, we use the DNN Logits. The DNN Logits is the intermediate result in the final layer. In our design, attacker will first select a specific input, then to collect a set of corresponding Logits value. This value set can be hard-coded or stored in the model parameters. Later, along with the testing tools, we can compare the present value with the recorded one. Once the Logits value matched, the malicious behavior is activated to extract and to execute the malicious code. These extract behaviors can be written into functions during the creation step or taking advantage of the insecure deserialization. To better handle input variation from physical world, we further improve the DNN Logits Trigger by matching the rank of Logits rather than the value. We will compare them later. For the code execution, we have many vulnerabilities in both hardware and software in machine learning system can be used to run the code. In our implementation, we use a dynamic execution for the demonstration purpose. We create the Stego-Net prototype on the Nvidia Jetson embedded device with two configurations. In lab configuration, we tested a bundle of mainstream DNN models and malware samples. In physical world configuration, we mainly evaluate the reliability of proposed trigger design under strong input variations. We evaluate the effectiveness of StegoNet, measuring the model accuracy of the payload injection. A good approach should be able to maintain the model accuracy close to the original value to avoid suspect. Compared to ASP, resilience training can better preserve the DNN accuracy even on the small-scale models. We found that if the portion of modified parameter is less than 12%, resilience training can perfectly rectify the model accuracy to the original value. Value mapping and sign mapping can perform even better, especially on the ultra-small DNN models. In particular, sign mapping can secure the original model accuracy on all testing cases. However, due to the limited data space on the sign bits, sign mapping is more efficient but less scalable compared to other approaches. We also tested StegoNet with the existing anti-malware and Stego analysis tool. Anti-malware can detect the selected malware samples with a high detection rate, but is not able to detect the injected payload in DNN model. We further test several Stego analysis tools. These tools can well detect the traditional Stego-Malware and the LSP injected payload. However, they are still inefficient to find the suspicious footprints of proposed DNN-oriented payload injection. The reason behind is the scalability and complexity of the DNN model. We further evaluate the injection reliability measuring the payload bit flipping rate under model fine-tuning. A reliable injection can protect the integrity of payload with minimal bit flipping rate, even on the extreme model fine-tuning. Our results show that sign mapping is the most reliable approach to protect the payload integrity, followed by value mapping and resilience mapping. To evaluate the trigger reliability, We measure the F1 score of different trigger designs under the augmented strong variation, such as camera angle, image distortion. The image class trigger, single class trigger used in neural Trojan is unreliable due to the high false positive rate. All process rank trigger performs better, however, cannot handle the ultra-strong variation after the fine-tune optimization by feeding the variation inputs into StegoNet. The reliability can be rectified even under the strong variation. That's the best approach. To conclude this talk, we show a new type of DNN-based malware using model parameter as a new injection channel. We explored two new attack vectors and show the unique design consideration on StegoNet compared to the traditional Stego-Malware. We propose a several DNN-oriented attack approach, and our results show that existing anti-malware and Stego analysis tools cannot defend the StegoNet. Mitigation techniques shall be revisited by synthetically considering the data, algorithm, software, and hardware in deep neural networks. Thank you very much.